Hey everyone, welcome! So today we're going to dive into the physics of motion in 2 dimensions. Yeah, I know, it sounds super complex, but trust me, by the end of this, you'll see how everything from a thrown baseball to trying to swim across a river follows just a few surprisingly simple rules.
All right, let's just start with the most basic question you can ask. You throw a ball, you fire something from a cannon, whatever it is, it follows this arc through the air. But how do we actually predict exactly where it's going to land? It just looks like this one single complicated curve, right?
Well, here's the secret weapon, the key to the whole thing. The most powerful trick we have is to stop looking at it as one big messy problem. Instead, we break it down. We're going to treat the forward motion and the up and down motion as 2 completely separate stories that just happen to be playing out at the exact same time.
So here's our game plan. First up, we're going to deconstruct 2D motion into those 2 simple parts. Then, we'll use that to master the classic projectile arc. After that, we'll look at some really tricky special cases, kind of shift our point of view with relative motion, and then finally, we'll put it all together to solve those classic physics puzzles with rivers and rain. Sound good?
All right, let's get right into it. This first concept, honestly, it's the foundation for everything else we're going to talk about. Any motion you can imagine in a flat plane can be understood as 2 separate, one-dimensional motions happening at the same time.
Okay, so check this out. This is the big idea. Horizontally, in the x direction, an object just coasts. Once you launch it, its forward speed doesn't change at all. There's no acceleration. But vertically, in the y direction, that's a completely different story. It's in a constant fight with gravity, which is always pulling it down with a steady acceleration we call g. And the key thing is, these 2 motions are totally, completely independent of each other.
And this is how we see it written down in the math, right? When you see a velocity written out like a vector, something like 6i plus 8j, it's really just a shorthand way of telling both of those stories at once. You can think of that 6i bit as the script for the horizontal story. Its job is to say, go forward at a steady 6. And the 8j part, that's the starting line for the vertical story, an initial upward speed of 8 that gravity is going to start messing with immediately. Okay, so now that we've got these 2 separate stories, let's see how they come together to create that beautiful, predictable arc of a projectile. By keeping these 2 stories straight, we can suddenly calculate pretty much everything about its flight.
Now, don't just look at these as formulas to memorize. What's so cool is how they tell the story we've been talking about. The time of flight, that's a purely vertical story. It's all about how long gravity takes to do its thing. The maximum height, also completely a vertical story about that upward journey. But the horizontal range, r, that's where the 2 stories finally meet. It's just that constant horizontal speed multiplied by the total time the object spins in the air.
And believe me, these formulas are super powerful. Let's take a real-world example from one of the problems, Q14. A cricketer wants to throw a ball for the maximum possible distance, which happens to be 100 meters. Well, using that range formula, we can figure out they need to launch it at almost exactly 32 meters per second. That's literally the physics telling you what it takes to make that perfect, record-setting throw.
Okay, so we've got the rules down. Now let's have some fun and test them with a few scenarios that, well, they might just mess with your intuition a little bit. These are the kinds of puzzles that show you just how deep these ideas go. Okay, get ready for a classic. This one's a real brain teaser, straight out of question Q6. Imagine you have 2 guns, side by side, at the exact same height. One fires a super fast bullet, the other fires a much slower one. They're both fired perfectly horizontally at the exact same instant. Which bullet hits the ground first?
The answer is neither. Yep, they hit the ground at the exact same time.
And this, right here, is the perfect illustration of our big idea. Gravity doesn't care one bit how fast you're going sideways. It pulls both of those bullets downward with the exact same acceleration. Yeah, their horizontal stories are wildly different. One goes way farther than the other. But their vertical stories, that journey from that height down to the ground, are absolutely identical.
Okay, so up until now, we've kind of been watching all this action from a fixed spot on the ground, like a spectator. But what happens when the spectator is also moving? Well, that brings us to our next huge idea, relative motion.
And really, it all boils down to this one simple, powerful idea. The speed and direction you measure for any object completely depends on your own speed and direction. There's no single true velocity. It's all about your frame of reference.
Let's make this super concrete with an example from problem Q52. If a train is overtaking a man running in the same direction, from the man's point of view, the train seems to be moving kind of slowly. Its speed is just the difference between their two speeds. But if they're running towards each other, from his perspective, that train feels like it's coming at him incredibly fast, at a speed that's the sum of their two speeds. Same train, same man, totally different perceived velocities.
All right, so now that we've got a handle on relative velocity, let's take it to the next level and apply it to some of those classic two-dimensional puzzles that physicists just love using to test our understanding.
So, picture this. You're standing on the bank of a river. You want to swim straight across from point A to point B. But there's a catch. The river itself is flowing sideways. Your own swimming speed and the river's current are going to combine to create your actual path. So how do you deal with that?
You've basically got two choices, two main strategies. Strategy 1, you want to get across as fast as humanly possible. To do that, you point yourself straight across the river and just go for it. But you're going to get carried downstream. Strategy 2, you want to travel the shortest possible path and land directly opposite from where you started. To pull that off, you've got to aim upstream, fighting the current just enough so that your real path is a straight line.
And here's the good news. Solving any of these river problems really just boils down to a simple 3-step recipe. Step 1, how fast can you swim if the water is perfectly still? Step 2, how fast is the river moving relative to the ground? And step 3, you just add those two ideas together using vectors to find out where you'll actually go. That 3-step logic is the key every single time.
And you know what's cool? This logic isn't just for rivers. Think about the last time you walked in the rain, like in problem Q68. If the rain is falling straight down, but you start walking forward, it suddenly feels like the rain is coming at you from an angle, right? Well, the angle you have to tilt your umbrella is a direct result of adding the rain's velocity vector to your own. It's all relative motion.
Okay, to bring this all home, I'm going to leave you with one final puzzle from question Q35 that perfectly ties together everything we've talked about: projectile motion and relative velocity. You throw a ball with a certain speed, and at that exact moment, you start running at half that speed to try and catch it. To make the catch, your horizontal speed has to perfectly match the ball's constant horizontal speed. So what is the one perfect angle you have to throw that ball at to make it all work? It's a fantastic problem. What do you think? Can you figure it out?